listeners to another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. Man, are we really going to be leaning into that intro, because we are going to be talking quite a bit about concepts, software, and procedures behind the software, because in case you missed it this week, the White House published a report about code assurance and encouraging memory-safe languages. So there's a lot to unpack there, and we're going to dive into it. But I gotta say, an F in the chat for C and C++, because, spoiler alert, the report kind of wants you to not use them anymore. Is it for good reason? Is it for not? We're going to get into that in this episode, so you'll definitely want to stay tuned. But first, let's get into this week's trivia question. So on the topic of memory safety, according to Microsoft and Google, what percentage of all security vulnerabilities are due to memory safety issues? So what percentage of security vulnerabilities are due to memory safety issues? And that is your trivia question for the week. Now, this episode is going to be fairly cybersecurity heavy with this whole report about memory-safe languages. And on the topic of memory safety, I figure we get right into this week's cybersecurity tip. As I mentioned, we're going to be talking quite a bit about cybersecurity in this episode, and one thing that's really critical when it comes to cybersecurity and software development in general, and kind of where those two mesh really well, is the idea of secure coding. And I'm pretty sure we've talked about it on the podcast before. It might have even been a security tip a while ago. But for the nature of this episode, seeing that it's talking a lot about memory-safe programming languages, I thought we kind of also bring up the fact of why you should be implementing secure coding in your software development from the beginning and not as an afterthought as it sometimes gets relegated to. So I guess first we should break down what secure coding means. So in essence, it's basically a set of things that you do in your through your software development process to mitigate the number of vulnerabilities that could potentially happen through various means. The first and one of the most notable is assuming all user input is malicious. Now, granted, not all user input is malicious, but if you take the mindset that all user input is malicious, it will help you to better defend against potential attack surfaces and vulnerabilities. For one of the big instances is if you are doing any kind of if you're using that user input for any kind of backend query or API query or SQL query or anything like that, if you are using that user input, you really need to verify that that user input is actually good, because if the attacker knows that what they're inputting goes right to an SQL database query, they can do what's called an SQL injection and essentially write their own SQL query as their input and perform that SQL query on your backend because you didn't bother to parse the input. So it's really important for that, but it's also important in things like buffer overflows are something that's probably going to come up quite a bit in this episode. But one thing that makes buffer overflows so dangerous is because once you overflow the buffer, if you properly format the text that you're copying into the buffer you're overflowing, you can essentially make the program arbitrarily jump to different sections of memory, which can then execute your arbitrary code. So that's another reason that you want to make sure that your user input is malicious. And I'm sure we could go on and on and on about why and examples of malicious user input and why you want to prevent against it. But we got a lot of other stuff to cover. So yeah, make sure you're assuming all user input is malicious and treating it and handling it accordingly. The next thing you want to make sure is that you have full test coverage of your entire code base, because one thing that's kind of a nightmare amongst devs is there's the saying out there where you fix or add one feature over here and then somehow that manages to break something else over here and you're not exactly sure why. Well, if you have full proper test coverage of all of your code, you can pretty quickly and easily identify where the errors are occurring, what's causing them, and especially if you have multiple functions that are calling each other, that's generally where the issue arises, because if you modify function foo and function bar is calling function foo, if you make a change to one of them, it could potentially have impacts on the other. So having full test coverage can help mitigate this, or at least show you the errors before you end up pushing that code to production, only to then realize that there is a potential bug or critical vulnerability. The next one is using memory sanitizers and memory checkers to ensure you're not going out of bounds, trying to access memory after it's freed, etc. Now, this is mainly specifically talking to non-memory safe languages, because other languages like Java or Rust or Go or Python or something like that, if you go out of bounds or try to access memory you're not allowed to, the program will just crash or throw some kind of exception or do something to prevent you from doing that. But if you're using something like C or C++, they're more than happy to let you do that, which is where a lot of memory-related vulnerabilities and exploits come into play. So one thing that these memory sanitizers and memory checkers can do for you is they can monitor the running of your program and basically see if you're trying to, say, access the n+1 element of an array, which is out of bounds, or maybe you're trying to access memory that had previously been freed and is, who knows what's actually there, if it's been reallocated, if it's still the same data, who knows. So, and it also, in addition to that, can also check for memory leaks as well. So there's a lot of benefits to using memory sanitizers and memory checkers in your development and in your testing to ensure that you don't have some of these easily to avoid issues. The next one, and probably the biggest one where a lot of the issues come in, is ensuring the data you're copying does not exceed your buffer. Again, here comes back to the buffer overflow. Now, there's a few different ways that you can go about ensuring that you're not copying more data into your buffer than you have allocated. The first one is to do stir copy if you're using like C, for instance. And the way stir copy works, if you're not familiar, is it takes in 3 parameters. The first one is the destination, so where do you want to copy the memory into? This is your buffer that you're copying into. The second parameter is the source, so what is the string that you're trying to copy into your buffer? And then the last one is the size, which is the big difference between regular stir copy and stir copy. So stir copy will copy at most the size you tell it. So generally, it's good practice to use stir copy, especially if you're dealing with data that you're not 100% sure is valid, because what you can do is you can say allocate, 64 elements into your buffer, and then you can basically call stir and copy and say, all right, I want to copy the data into my buffer from the source, and I'm copying 64 elements, right? 64 bytes. So what this basically allows you to do is you'll either copy the entire length of your source, or you'll copy 64 bytes worth, and that way you ensure that you don't overflow your buffer. So that's one way you can do it. Another way, well, I guess one slight issue that you do have to be mindful of with stir and copy is you're not guaranteed to have a null terminator at the end. And basically all that means is in the world of C and like C strings are ended with a null terminator, which is essentially just a 0. And that basically tells every single string-related function in the C standard library where to end. So if you don't have a null terminator, you can easily run past the end of the string and do stuff off in memory and insert more memory-related issues. So that's one thing you'll have to be mindful of. So it's generally best practice to essentially get the length that you copied in -1 and then add a null terminator there just to ensure that your string ends in a null terminator. Going on to the other way you can do it is you can dynamically allocate the amount for your buffer. So essentially what this means is if you're, say, dealing with C++, you can use the functions built into the string object, so either like a dot length or dot size. Or if you're using straight C, you can do something like stir nlen, which basically says I want to get the string length up to a maximum number of characters. And the reason why you'd potentially want to do this is because, like I said, while strings are supposed to end with a null terminator, if someone's being malicious, it might not necessarily end in a null terminator, or if you didn't copy the data correctly, it might not end in a null terminator. So there's a couple instances where that could happen, but generally speaking, if you're getting user input through, say, like the command line, you could use something like getLine, which will automatically tell you the size of the data that got passed in, so you'll know how big of a buffer you'll need. And then what you can do here is, well, actually, if you're using getLine, you wouldn't even necessarily need to copy it into another buffer. But if you needed to, you would already know the size, and then what you can do is you can dynamically allocate memory through something like malloc or something like that, and doing the size that you got back +1. And the reason why you want to do the +1 is because the size doesn't account for the null terminator, so you have to account for that doing the +1, so then you can append a additional null terminator just to be on the safe side. So just kind of some best practices there. And if you're copying strings, like I said, best practice to always add a null terminator regardless of if you know the string has a null terminator or not, just to be on the safe side. And the other one related to string-related stuff that people will often run into issues with is using stircat, which is string concatenation. I believe there's also stirncat, which is similar to stir and copy. You only copy or concatenate up to a certain amount. But regardless, with stircat, you also want to make sure that the string that you're appending has enough size associated with it to accommodate the string that you're trying to append to it. So if you only have, say, 5 bytes left on your string, you'd want to make sure you resized it before you appended, say, 25 bytes onto the end of it, because then you would run off and overwrite additional memory, and yeah, bad things happen. So those are just some of the things that you kind of want to talk. Well, that's kind of some of the things that we talk about when we're talking about secure coding. Just ways to prevent against these, memory-related issues, protecting against user input. And the user input, I would say, is the one that's most universal out of all of these. And obviously, I guess the fuzzing tools, which is basically a way to test garbage input into your program to make sure it can handle all the various nonsense that people will try to pass into your program. So some of those things in the beginning are very universal, but the things specifically related to like string copying and all that stuff is more C and C++ related. But those are the kinds of things that we're talking about when we mention secure coding, because a lot of the times, at least I think, it's kind of an afterthought. You just kind of implement it, get it working, and then bugs come up as they may, and they sometimes are related to memory safety issues, and yeah. But anyway, secure coding, that is your cybersecurity tip for the week. And before we get into the report, I want to touch on briefly what nerdy stuff have I been up to this week. So again, a lot of the same when it comes to the video game I'm working on. If you can't guess by that, more refactoring, of course. And I got the save screen from the options menu, got that implemented and working, so I was pretty pumped about that. But probably the biggest and feature I'm most happy with at the moment is that my game is now officially multi-threaded. And I say officially because I'm pretty sure Raylib probably does some multi-threading behind the scenes, but I'm not including that because that's not anything that I did. So I officially implemented multi-threading, and I did this in a couple of ways. The first one relates to the save screen saving of the data, which honestly is 100% overkill, if I'm being honest, at least at the moment, because when I first implemented it, I actually kind of did it wrong in the sense that I spun off the thread and then waited for the thread to finish before joining back and continuing through the main loop of the program. But I didn't notice it because, of course, I mean, there's really nothing to save at this point, so it's very quick. So that wasn't really a good test. But I did later end up fixing that, so it actually works like it's supposed to. But the main reason I kind of wanted to do that was in the off chance that something happens and saving takes a little while, the game doesn't essentially freeze before continuing on to the next portion of the dialogue saying that you're saving. Because where I start the save call and kick all that off before I actually print out that you're saving. So if for whatever reason you ran into an issue, you would just kind of freeze, like after you hit the yes, I want to save button. So yeah, so just kind of on the off chance, threw it out in there. Plus, it gave me an excuse to add multi-threading. But the second one is something I'm more, I guess, optimistic about of its future implications. So I basically created what I called a background manager object, which will essentially manage all the various background processes that need to go on during the runtime of the game. So currently there's only one at the moment, but the idea here is to essentially spin up different threads for all the various processes that have to go on in the background. So currently, as of right now, the only thing that exists there is a thread to keep track of game time. So I think right now I have it set for 10 seconds, although I might end up changing that. But basically every 10 seconds, or if the program ends, if it ends, obviously it'll just exit, but otherwise, like every 10 seconds, it'll add 10 seconds to the game time and just constantly update that. And then I have two functions in there, one to start all the threads or start all the background processes, and then one, of course, to join them back up and make sure they all exit properly. So I was pretty hyped about that because I think that's going to have a lot of future implications that'll be definitely very beneficial, and kind of having that groundwork laid is definitely going to be a positive. And not really on features, but one thing that really confused me, at least initially before I dug into the source code, was a very peculiar bug that I ran into on Windows. So I was doing some testing between the various operating systems because, of course, this is supposed to be a cross-platform game, and if the game doesn't work on one of the systems, that's kind of an issue. So I was doing some testing, and I noticed on Windows it would hard crash, not as bad as that crash we talked about a couple weeks ago on Linux with the dialogue. That was horribly crashing. So this was crashing, but not quite as badly. But it was crashing pretty hard whenever I was trying to run any of the save or load game tests, which I found rather odd because I'm pretty sure I never had that issue before, and this is only recently that it happened. So it turned out what the issue was I was calling the vanilla free function from the standard library and not the internal mem-free function that Raylib provides and tells you to use if you use their compress and decompress data functions, which I happen to be using in this case. So to their credit, if I actually listened to the documentation and used the proper function that I was supposed to use, I wouldn't have had this issue in the first place, because it plainly tells you that if you're using the compress and decompress data functions, that you have to use mem-free. And so technically it's my own fault for not reading the manual. But the thing that confused me, though, was, one, I hadn't ran into this issue before. Two, it only happened on Windows. And yeah, I was just confused, because what even confused me more was when I looked at the Raylib source code. They have they call it their own custom allocator, but in essence, it's basically just a wrapper for the malloc, calloc, realloc, and free. That's literally all it's doing under the hood. If you look at the source code, their internal allocators are essentially just macros that call those functions from the standard library, which is why, when I would call free, it wouldn't have any issues, because that's all the mem-free would do anyway. It would just call free. So I had to think about this one, and then I eventually came up with a theory, which I'm not 100% sure, but this is my best guess as to why I run into this issue on Windows. And it partly, I think, stems from the fact that I compile the Raylib library with one compiler, and I build my game with a different one, which it's kind of complicated, but the short version is Raylib doesn't support MSys2, and which MSys2 is what I use to build my game. But Raylib does support MingGW, which you can install via MSys2. So what I did was I just compile using MingGW. I compile a DLL of the Raylib library, so I can basically create a shared object that I can compile against. And the reason why I don't create a static library, which would essentially get compiled into my executable, is because MingGW and the MSys versions, they don't work together, so you get a bunch of errors, and it was just easier to create a DLL. Anyway, my assumption is, because these two are different and they're not technically compatible with each other, my assumption is the free implementations of the MSys2 variant and the MingGW variant are different. So when you try to call the MSys2 free on memory that was allocated by the MingGW malloc, they're not compatible. Just like when you are in C++ world, if you use new on something, yeah, free might be able to free it, but you're not guaranteed, because C++ essentially doesn't make the guarantee that the allocation is going to be from malloc. So there's a chance you might be able to use free and get away with it, but you're not guaranteed, which is why you're supposed to use delete when you call new. So I'm assuming it's a similar instance here where the allocation is done slightly differently, which is why free doesn't work, but is also why I don't have any issues with free on macOS or Linux, because the compiler that I use to build the library is the exact same one that I use to build the executable. But they also kind of get bundled into the same executable, so I don't know if that plays a role either. But I think mainly it's because it's from the same compiler, so the allocation and freeing is the same. But regardless, I just decided to switch to what the manual recommended and use mem-free. So kind of a wild learning experience, but that's at least my best guess of why I ran into that issue. But yeah, so I think with that, we should probably get into the main story of the week, which is the White House publishing a report which they called Reduce Memory Safety Vulnerabilities at Scale. Creators of software and hardware can better secure the building blocks of cyberspace. So I'll have the full report linked down in the show notes, and it is, I think it's like 19 pages or something like that. So it is a fairly substantial document. But first, I guess before we get into the report, it talks about this idea of memory safety. So I think first we should kind of define what memory safety is. So the technical definition is the state of being protected from software bugs and vulnerabilities dealing with memory access. And to be honest, that doesn't really tell us too much. I mean, if you're technical, that explains it perfectly, but if you don't come from a technical background, that probably just sounds like more tech jargon on top of memory safety, which may also sound like tech jargon. So let's put this into some practical terms. So in C and C++, if you allocate a buffer of 32 bytes, but copy 256 bytes into your 32-byte buffer, the language will allow you to do this and essentially overwrite the data beyond your buffer, which is referred to as a buffer overflow. However, in other languages like Java or Python, for instance, which are memory safe, they don't allow you to do this. So if you try to do it, they'll throw an exception and just crash the program. Now, granted, the C and C++ versions will most likely crash the program, but it's not guaranteed because, as we mentioned previously, buffer overflows can potentially allow attackers to jump to arbitrary memory addresses and run arbitrary code, and there's a whole lot extra to it. But yeah, so Java, Python, and other memory-safe languages, if this ever happens, they'll just crash and don't allow you to overwrite memory that you shouldn't be. Rust also has this capability through its borrow checker, which also can handle all the stuff dealing with memory allocations, freeing operations, and the like. And as I kind of alluded to here, in C and C++, there is no bounds checking whatsoever. So C and C++ will be more than happy to let you go beyond the bounds of your array that you have allocated and either keep on writing to it or reading from it, getting arbitrary memory or writing to arbitrary memory. Whereas if you're doing it in, say, Java, for instance, you get the infamous array out of bounds error or exception. So that's basically essentially what we're talking about with memory safety. Do the languages allow you to write to memory you technically or aren't supposed to be, or do they freely let you kind of do whatever you want? So that's kind of the core of memory safety. So with that, let's get into the report itself. So the report starts off by mentioning how cybersecurity is very much a reactionary exercise, and we're always reacting to vulnerabilities, and they're basically calling out the tech industry and software developers to focus on securing cyberspace by writing secure code and creating more secure hardware. So this is definitely true. I mean, you don't have to look too far into the news to hear about all the various, vulnerabilities that crop up like essentially every day. And kind of as we alluded to, and we'll get to kind of some of the reasons why a little later on here. But it is companies kind of sort of don't seem all that incentivized to implement, super secure practices into their coding. They just kind of want to get the features out the door and get the updates, keep the updates flowing and all that stuff. But they go on to say proactively eliminating an entire category of software vulnerabilities is essential to reduce the burden on end users and protecting against cybersecurity threats. And to be honest, 100% agree with that sentiment, because they even reference a report by both Google and Microsoft that say that around 70% of the vulnerabilities are due to memory access issues. So if you imagine all of the vulnerabilities that crop up, granted there's a lot of them, but if you imagine you removed 70% of those, not only would it make the developers' lives a lot easier because they're not having to react to the latest zero-day exploit and having to figure out a patch and getting that out as quick as possible. Granted, there are still potential issues where there could be zero-day exploits like that would occur. But if you remove 70% of those vulnerabilities from memory issues, that is a ton, especially when we're talking about how many kind of vulnerabilities are out there. So I think that is definitely an excellent point that the report mentions. And then they also go on to talk about some of the hardware-related approaches as well, specifically memory tagging extensions and the capability hardware-enhanced risk instructions to reduce memory safety vulnerabilities, especially in space systems. So these are kind of two pretty cool solutions. We'll get into that capability hardware enhanced risk instructions a little later on, but the memory tagging extensions is pretty cool because essentially what that allows you to do is track objects essentially track objects in memory. So for instance, if you had a person object and then you later tried to reference it as an automobile, the CPU itself will throw an exception and essentially crash the program, which is a pretty cool way to get around some of the lax nature that C and C++ kind of allow you to just willy-nilly access memory even after you freed it, for instance. So this would be kind of a good instance of kind of a potential use after free instance. So memory tagging, definitely a good hardware mitigation there as well. They go on to say, adopting memory-safe programming languages remains one of the most impactful actions, which this is totally true because it's a lot easier and cheaper to write code than it is to replace tens of thousands of servers in a data center with new hardware. So it's a lot easier to write an application in, say, Rust or Go than it is to replace your entire data center's worth of computers just to make it more hardware secure so you can continue running your potentially memory-unsafe code in your C and C++, right? So from that perspective, it's definitely true that it is not only the most impactful way to make changes, but also potentially even the most efficient and cost-effective as well. So they also go on to advocate that companies' executives should prioritize software security and cybersecurity quality metrics as a business imperative for informed investment and risk mitigations, which this is honestly another good point because a lot of the times, like the report even mentions, that cybersecurity kind of seems to be an afterthought and companies don't necessarily prioritize that. So they kind of want, let's get this feature out the door rather than, all right, let's pump the brakes for a second and make sure that this feature doesn't have any glaring security bugs or vulnerabilities lurking in there. Maybe we could have the due diligence to run it through some scanners to check for known vulnerabilities, run it through some fuzzing tools to make sure it can handle just random garbage user input. Let's check to see if use some memory sanitizers to check to see if we're going out of bounds on some of our calls or our writes. Things like that honestly, you could easily integrate into a CI/CD pipeline or continuous integration, continuous deployment pipeline. You can automate automate all that stuff so you don't even have to have someone manually testing these things. So definitely a good thing that companies should do. We'll see if it actually ends up panning out. And then just in general, they call for overall pushing for cybersecurity and cybersecurity metrics to take on a larger role in the development process. So kind of, I guess, if there was only, if there's only one software development methodology that did this, something like, so how like DevOps, right, is supposed to be this automated way where you develop your code and then use CI/CD pipelines. And if only there was a methodology that existed that was like DevOps, but also included security. So hopefully you could catch the dripping amount of sarcasm coming from my voice there, because of course this does already exist, and that is through DevSecOps, which essentially takes all the properties of DevOps but includes security in there as well, to kind of add that security component that the report is referencing. So that was kind of the report in a nutshell. I will have the full report linked in the show notes if you care to read it. But first, I think I want to break down some stuff and kind of get into some things that I kind of alluded to. We'll get back to, and then some of my additional thoughts. So first, I think we need to start off with a technicality. So assembly language and machine code are inherently not memory safe. And which I guess we can caveat that with those CPU architectural changes from the compatibility hardware enhanced RISC instruction architecture, which I referenced before. And basically what this is claiming to allow you to do is allow historically memory unsafe languages the ability to adopt and provide, quote, provide strong, compatible, and efficient protection against many widely exploited vulnerabilities, end quote. So basically, they kind of built in protections into the CPU architecture itself to essentially prevent you from doing some of these, memory unsafe things. So assuming you're not using, some kind of architecture like that, but even if you are, you could probably still get around some things. But in essence, assembly and machine code is memory unsafe. So but the reason why I bring this up here is because technically speaking, the only code that can run on a CPU is machine code. So it doesn't matter what language you use, somewhere in that sausage-making process, it's getting converted to machine code to run on the CPU. So whether you are using something like a compiled language that compiles down directly to machine code before you run it, whether you're using an interpreter, whether you're using something like Java that compiles down to bytecode, which then gets run in the Java virtual machine, which then translate those instructions to machine code, whatever the case is, at the end of the day, you're running machine code, which in essence is not memory safe. So with this in mind, you could technically argue that nothing is memory safe since it all gets compiled down to machine code, which is not memory safe. So that's the technicality. But if we're being honest, that is pretty disingenuous, because just because a language isn't memory safe doesn't mean code written in that language is not memory safe. So in essence, you can write completely memory safe code in a non-memory safe language. So yes, that means that you can write C and C+ code that is memory safe, even though C and C++ is not a memory safe programming language. So one thing that the report specifically calls out is Rust. They specifically actually name drop Rust, which that, from what I remember from the report, they only name drop, I believe, 3 languages: C, C++, and then Rust are the only ones they name drop. Although they do reference memory-safe languages, but they don't specifically define those, although they were defined, and I think it was in a 2022 paper or blog or something published by the NSA of some memory safe languages. But Rust gets specifically called out as a memory safe language, which it is. But inevitably, Rust also gets compiled down to machine code as well. The only difference is the Rust compiler will add checks for and potentially catch memory unsafe pieces of code, kind of through that borrow checker like we talked about earlier. But of course, this is ensuring that you didn't label the code as unsafe. So essentially, Rust has this unsafe keyword, which is required for certain use cases. Specifically, a couple examples. One, if you're writing inline assembly for embedded systems, which if you want to completely remove C and C++ entirely, you're going to have to deal with embedded systems, and at the end of the day, somewhere along the line, you're going to need to write some assembly. So you can do that in Rust, but you have to use the unsafe keyword. So you would be using the unsafe keyword there. And also, if you're trying to interface with things like C or C++ libraries, that would be another instance where you would have to use the unsafe keyword. In any case, using the unsafe keyword can actually allow you to dereference raw pointers. So in English, what that means is you essentially, so we've talked before about pointers, and pointers are literally just a memory address. So this is a variable that has a number in it, and that number is a location in memory. When you dereference the pointer, essentially what you're doing is you're going to the memory address that the pointer is pointing to and getting the data that is located there. So that's what we're talking about when we say dereferencing a pointer. So when you dereference the pointer, this could potentially lead to undefined or exploitable effects depending on what's located there. So there is potentially still a chance that Rust could encounter issues like this, but generally speaking, Rust is still considered to be memory safe. One thing that I did find a little interesting about the report is they talk about the requirements of space systems specifically, which require: 1, languages must allow code to be close to the kernel and tightly integrated with software and hardware. 2, they must support determinism, so timing outputs are consistent, which obviously you want to make sure that you have consistency, and timing is definitely a big thing, especially for space stuff. And 3, it must not have or be able to override the garbage collector. And we've talked before about garbage collectors, but essentially the garbage collector reclaims memory that's no longer in use. To this, they say, quote, Rust, one example of a memory-safe programming language, has the 3 requisite properties above, but has not yet been proven in space systems. Further progress on development toolchains, workforce education, and fielded case studies are needed to demonstrate the viability of memory-safe languages in these use cases. End quote. So, on the one hand, they're kind of implying that, like, yes, Rust, we're going to use Rust. It has everything we want. But on the other hand, they're like, well, we haven't really determined that it's viable and is going to work, so we kind of need to do further testing. So, yeah. So to me, this is kind of like, it's good, that they're planning on using Rust, but they say further progress to demonstrate the validity. To me, seeing that this is the government we're talking about, this is probably going to be at least a few years, if not a decade plus, before they potentially would even get around to implementing Rust into like the space systems, which hopefully I'm wrong about that. But, knowing, just in general, the government isn't exactly the most fast moving, especially when it comes to technology. Call me a little suspect on how quickly that's actually going to be implemented. Now, they do rightly acknowledge the fact that even if you use a memory-safe language, that doesn't mean vulnerabilities won't exist, because There's logic errors. There's things like SQL injections, which could still happen regardless if you're using a memory safe language. So there are definitely still instances where a memory safe programming language won't fix all your issues because, like we've said many times, there is no silver bullet when it comes to cybersecurity. They also credit to them the vast majority of vulnerabilities, like I mentioned earlier, that Google and Microsoft study, and then further into that I think it was in the same study they referenced, depending on the application suite, anywhere from 60 to 90% of the vulnerabilities were due to memory safety issues, but of course that average being around 70. And of course, C and C++ being by far the biggest culprits. But the thing that I think we need to ask ourselves here is, whose fault is that, though? Is it the programming language's fault, or is it the programmer's fault that there are so many of these memory safety vulnerabilities with C and C++? Because yes, C and C++ are not memory safe. We've discussed this kind of at length, all the various things you can do, like, buffer overflowing the buffer, accessing memory that doesn't exist. There's a lot of things that you can do which totally makes C and C++ not memory safe. But as we mentioned, just because they're not memory safe doesn't mean you can't write memory safe code in these languages. Now, there's a common debate out there of if this is a skill issue. And I'm on the fence, and I kind of understand both sides. But regardless, when it all comes down to it, I do kind of blame the developers, because it's not the language's fault that the code you wrote is vulnerable to, some kind of exploit. Because at the end of the day, the language didn't write the code, you wrote the code. So at the end of the day, it is the developer's fault. But obviously, the statistics show that putting the task of writing secure code in these languages on the developers isn't working, because C has been around for like 50 years now at this point, and these memory-related vulnerabilities have not gone away whatsoever. So is that the developers? You would think if you've been writing in a language for 50 years, you'd probably get pretty good at not having, memory vulnerabilities. So while, yes, technically it's a skill issue, that doesn't excuse the fact that this has been going on now for basically half a century, right? Yes, you can make the argument that is a skill issue, and you are correct, but at the same time, you can't use that as an excuse for the fact that this quote-unquote skill issue has been going on for 50 years at this point. And I also think that in the hands of a skilled C and C++ developer, there wouldn't be any memory safety vulnerabilities at all, because they would have the forethought to check for things like buffer overflows or out of bound accesses, for example. So this kind of is one of the big issues with the report, because one of the big problems with the proposal is legacy code, which in fairness, the report does touch on legacy code, but the thing is, how much code out there is written in C and C++ that exists? Because there's a lot of it. There's definitely a lot. Now, what about memory safe languages, written in there are issues potentially with these memory safe languages, because what about the memory safe languages that are written in languages that are not memory safe? And what I mean by this is Python is a good example. Some of the core features of Python are written in C, But Python is deemed to be memory safe, but the underlying code that created Python is not memory safe. So I guess technically in theory, you might be able to argue that this could potentially introduce some memory unsafety. Similarly, Java, which is also known as a memory-safe language and known for its garbage collector in the Java virtual machine, parts of Java, the programming language itself, were written in C and C++. So, and it's not limited to just these two languages. Those are just two that I happened to find without too much effort into looking. So some could potentially argue that if there's so much code in production, both written in memory unsafe languages and potentially languages that are written in memory unsafe languages, what does that really mean? But specifically, I want to come back to the legacy code aspect, because so much of the code that's in production now across the globe through data centers and everywhere is written in memory unsafe languages, and you can't just rewrite everything. I mean, some smaller applications or small critical pieces of the code base you could potentially rewrite, but then you kind of have to go back through the whole process of recertifying that code actually functions as you expect it to and won't break other components, which again, if you have, that vast suite of test cases to verify all this stuff, it really shouldn't be a huge issue. But at the end of the day, that is something that you have to go through, validate, and test. Now, I hear some of the Rust evangelists out there when I pose the question of, do you really want the entire Linux kernel and Windows to be completely rewritten in Rust? Of course, the Rust fanboys would say absolutely yes. And one of the reasons I leave Mac OS out of that and like FreeBSD and all that, because FreeBSD and other Unix-based operating systems are also largely written in C. But the reason I kind of left out Mac OS is because I know well, first off, I have no idea what it's technically written in. I'm assuming there's a lot of C, but I also know Mac OS loves using Swift also, which, funny enough, is actually deemed a memory-safe programming language, but I would assume there is probably also a good amount of C and C++ in there as well. But unlike the Linux kernel that's completely open source, or old versions of the Windows kernel that happen to be leaked to the internet, it's kind of hard to get the macOS source code or any previous version of it. Now, I'm sure... Now, granted, the Linux kernel has recently introduced Rust into the Linux kernel, so there are portions of the Linux kernel that are written in Rust. Not sure about Windows, but I know like C#, I think, is a fairly Windowsy thing, I think, and C# is again another one of those memory safe languages. But regardless, there is still a lot of C in those operating systems. And when it comes to operating systems, do you have any idea what kind of a Herculean task it would be to completely rewrite an entire operating system while also preserving all the functionality of the said operating system, while also continuing to make improvements to the operating system in a memory-safe language? I mean, that would just be absolutely insane to do. You essentially have to more or less start from ground zero, and operating systems comprise of millions, if not tens of millions, of lines of code. And at some point, you're going to have to write assembly, because at some point there's just no around it when you're dealing with things like interfacing with drivers or writing like bootloaders or that kind of thing. There are some things where you just can't get around. You have to write assembly, which, granted, the report, credit to the report, it does actually acknowledge this fact, that there are some situations where using a memory-safe language is not feasible, and this is kind of one of them. But in general, the idea of having to rewrite an entire operating system especially widely used ones like the ones we mentioned, Linux, Windows, and Mac OS. I mean, that's, to be honest, it's not going to happen. And one of the reasons why we can see that it's not going to happen is you have to look at the return on investment of doing so. Especially what you have to put your head in the mindset of these companies. Since while yes, it would be good, to completely rewrite these operating systems into memory-safe languages to reduce a lot of the vulnerabilities that come up, there's just really not much of a return on investment there, because yes, you can mitigate memory safety vulnerabilities, but from the bottom line perspective, is it more cost effective to keep patching things and as the bugs come up, or spend the millions, if not billions of dollars on man hours and developers' time, diverting that away from features to continue improving your operating system, fixing bugs, all that stuff, into completely rewriting the operating system in a new programming language? And this isn't just for operating systems either. It's also for any kind of application, whether that's a desktop application, something that's running on a server. Regardless, the time it would take, both in man hours and money, to completely rewrite these massive monolithic applications is quite honestly not feasible for these companies, because you have to look at the side effects, right? You take away valuable resources, all the developers that you have to, put on this project and completely rewrite it. That takes away resources from implementing new features or fixing bugs and creating patches for vulnerabilities. Is it, for the company's perspective, it's a lot cheaper to incrementally fix bugs and patch vulnerabilities than completely rewrite everything. And I think a good way to kind of put this in perspective is with a little bit of a home lab analogy. So now we kind of hit the full trifecta on this episode, where we've talked about cybersecurity, software development, and now home labbing. So we got all the big three. That wasn't actually intentional, by the way. I just figured a home lab analogy would work well here. So we talked kind of about the cost effectiveness and why, while it's a good idea to rewrite all these things in memory safe languages, it's not cost effective. And the home lab analogy is this: is it better to keep the system you have or migrate to a more power efficient one? Because yes, the more power efficient one will save you money in the long run, but how long do you have to wait until you can reap those benefits? Because while yes, you might save 20 watts, an hour, or for instance, if it takes you over 7 years to recoup the cost of buying the system in energy savings, was it really worth it? Because you have to think about the upfront cost of buying the new system to replace the old system. How long is it going to take before you actually, get the return on your investment and actually end up saving money? Because yes, power inefficient systems can really drain your bank account. I'm not arguing that at all. But what also really drains your bank account is buying a completely new computer or new server. So you kind of have to do a cost-benefit analysis of, is the amount of power I'm going to save on this new server worth the amount of time it's going to take before those amount of savings actually pay for the server itself? So that's essentially the calculus that has to go into these companies when they're have to weigh the pros and cons of, do we completely rewrite this application in Rust, or do we just keep making patches with how it currently is in C and C++ and just deal with the vulnerabilities that come up as they may? Now, I'm not saying that you shouldn't rewrite memory unsafe code into a memory safe language. all I'm saying is there is a massive risk-reward, cost-benefit analysis that goes into a decision like that. Now, the report is obviously pushing for executives to prioritize this, but this also kind of poses the question of should all future code be written in a memory-safe language and not C and C++? And I guess the bigger question is, should C and C++ die? Should it, as the title of this episode suggests, start climbing the stairway to heaven? Or are they knocking on heaven's door? Can I insert another 80s and /70s rock song into this? Maybe, but I'm not going to. We're just going to stop it there. So getting back on track here, the report essentially does call for all future code, at least it recommends, that all future code be written in memory-safe languages and not C and C++. But that doesn't necessarily mean that, well, first off, it doesn't mean that C and C++ are now dead, because, as we mentioned, there are massive code bases out there and still tons and tons of code that is written in these languages, so it's not like they're going to be going away anytime soon. But also, as we discussed a couple weeks ago, C++ is making some great strides into eliminating memory errors entirely. Now, obviously, you can still introduce them, but if you're using things like the standard template library containers and smart pointers, kind of like what we talked about a few episodes ago, it's really hard to introduce some of those commonly known memory-unsafe vulnerabilities. Because if you're using things like smart pointers, they deallocate themselves when they go out of scope. If you're using the containers like vectors or maps or things like that, you don't have to worry about any of the memory allocation or memory management that goes into that. They kind of all handle themselves. So, I mean, you really have to try to insert, memory unsafe vulnerabilities into, if you're assuming you're using the standard template library to its fullest extent, of course. And the other thing with C and C++ too, one of the benefits of them having been around so long is that there's basically a compiler that exists for every conceivable platform, essentially, which cannot be said for other languages. So, for instance, there might be instances where if you need code to run at all on a system, C or C++ might be your only option, which, again, credit to the report, it does reference there are instances where a memory-safe language might not be feasible, but that would be a good instance where C and C++ might be your only option because of the system you're building for. That's the only language that can compile for it without you having to write your own compiler. But as we've seen, developers obviously can't be trusted to write secure code in these languages because, 50 years we're still having the same problems that we've had for the past 50 years. But I think with proper code coverage and testing through things like fuzzers, sanitizers, memory leak analyzers, that kind of a thing, a lot of memory unsafe vulnerabilities can be identified and eliminated before it even goes into production, and you wouldn't have to worry about, patching all these patches after the fact. But again, that still kind of relies on kind of a mindset shift in some of these companies, which the report does rightly address, that it kind of has to come from executives, pushing things. They can't just say, we need features, we need features, we need features. They should also prioritize things like, all right, let's make sure that our code, we're properly testing, properly checking the code, running it through, all these various testing suites to ensure that our code does not have any node vulnerabilities before we just hit full send it to prod, and just hope and pray that nothing happens. So I think there's definitely some ways that we can still use C and C++ and seriously mitigate the number of memory safety vulnerabilities. But again, that will take still will take kind of a culture shift from, the standard, I guess, DevOps idea of, all right, I'm just going to build my code, push it, and deploy it, versus to more of a, all right, I'm going to build my code, build it, test it, check for vulnerabilities, run it through a security suite to make sure things are good and there aren't any kind of known vulnerabilities or anything like that before we push it to production. So I think, adding those additional steps, while it might not make for as fast of releases, it will hopefully reduce the number of vulnerabilities. So I guess kind of wrapping up here, the TLDR, or I guess the TLDL, since this is a podcast, or the too long didn't listen, is the White House is recommending that all new tools and applications and software be written in NSA-approved memory-safe languages, so languages like Rust, Go, Java, JavaScript, C#, Ruby, and Swift. And where possible, pre-existing critical code should be migrated to a memory-safe language. In general, for existing code bases, adapt some kind of hybrid approach by implementing new functionality in a memory-safe language. And companies and developers should adopt best practices, kind of like those that we mentioned previously in our cybersecurity tip, to mitigate and reduce the attack surface. So I guess at the end here, they recommend that, should move to memory-safe languages and where possible, rewrite existing code bases that are in memory-unsafe languages into memory-safe languages. So does this mean I will be rewriting my video game or the rest of it in a memory-safe language? Absolutely not. I am going to continue to write it in C, more specifically C++. And in part, that is because there's a couple goals for the video game. One of them specifically being so I could improve my skills in C++ and just become a better C++ developer. And it's kind of hard to meet that goal if I switch away from C++ into a different language, and it would kind of defeat the purpose. So no, I will not be migrating. But I think overall, my thoughts of this report, I think in general, it kind of touches on a lot of things that, people that have been in the security space have been kind of saying for a while. We should be implementing, best practices into the software development procedures, not just, testing to see if it works and then pushing it and not really thinking anything more until a vulnerability or a bug pops up. So better testing code. And then as far as the memory-safe languages, I think, to be honest, it's probably the best move, because while I personally still really, really like C and C++, I mean, like we mentioned, there's so many memory unsafe, vulnerabilities related to memory safety in these languages, and it's obviously not getting any better through the past 50 years of C being around, and I don't exactly foresee it getting any better in the next 50 years. So I think by forcing developers to move to memory-safe languages, it's probably for the best in the sense that, we're just completely eliminating all those vulnerabilities, that entire subsection of vulnerabilities. Now, obviously, that's not going to remove all vulnerabilities, as we've mentioned before and as the report touches on. But this also doesn't mean that C and C++ are going to be going away anytime soon, because, like I mentioned, so much code out there exists, both in legacy applications and new applications that are written in C and C++, and they're not going to be going away anytime soon. They're not going to be rewritten anytime soon. So there's still definitely going to be a demand for C and C++ developers, because heck, there are still instances of COBOL in production, and that language is even older than C is and hasn't been taught for, I don't know how long. So there's definitely going to still be a need for C and C++ developers. I still think it's they're still both languages I think are worth learning. And I think if you can learn the languages and become proficient in them and not write memory unsafe code and, take the properly, proper checks, adding the proper checks in your code to make sure you're validating the user input, ensuring you're not going out of bounds, ensuring your buffers are large enough, all the best practice that we kind of talked about, you'll make yourself a pretty valuable programmer. So I don't think they're going away anytime soon. But I do also kind of agree that if we want to truly eliminate this large section of vulnerabilities, moving to strictly memory-safe languages is probably the only way to go if we truly want to remove them, because all the testing and all of the, we can only do so much, right? At the end of the day, companies are going to do what companies are going to do. As we've seen in 50 years, developers still write memory vulnerabilities into their code. Still happens. So if you can just completely eliminate that just by a choice of language, I mean, it's kind of hard to see the downsides as much as I love C and C++. So that was the report. Let me know what your thoughts are at my email, contact@darkassassins.com. If you have any questions about this episode, topics for future episodes, interested to hear your guys' thoughts about it. I can already tell if the Rust developers are going to be all up, just hooting and hollering, cheering. They're probably loving this news for sure. So before we go, let's get back to our trivia question for the week. Now, I intentionally made this trivia question the way it was, and hopefully you were listening attentively to this episode, because even if you didn't know the answer at the beginning of the episode, I dropped the answer a couple of times throughout the episode, so hopefully you were listening, and this should be a gimme for everyone. And this week's trivia question is, according to Microsoft and Google, what percentage of all security vulnerabilities are due to memory safety issues? And if you said 70%, congratulations, you were listening, or maybe you just knew it previously. Either way, congratulations on getting this week's trivia question correct. And if you enjoy this episode, definitely give it a rating and review and share this around, because this is definitely something that people need to know about, especially in the developer community. This is potentially a big shift, although let's be honest, probably not a whole lot's going to change, but it is definitely good food for thought. If you have any questions or comments about the episode, shoot me an email at contact@darkassassins.com. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bull nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.